And again, can someone just talk into the mic real fast? So
Hello, hello. Testing.
okay, good. Okay. Sorry. Like I said, my computer is just all kinds of wonky today with the update. And so I'm working on the little screen instead of on my big external monitor. Okay, so on Monday, we talked a little bit about phase transformations in the iron-carbon system, also known as steel. And we talked about mostly just plain carbon steel, where we're, as metallurgists or material scientists, we're most interested in what happens around the eutectoid point, because that's what drives our final microstructure. Because most of the time we're doing some kind of heat treatment process where we're holding in the austenite gamma phase field for an extended period of time before coming down. The 50% of you in the class that are in the welding engineering program, you care almost as much about what's going on at this paratectic reaction, because when you're doing fast cooling from a melt pool, like you do in a fusion weld situation, you typically will not spend as much time in this gamma region to erase the microstructural aspects of what's going on up here. I'm not going to get too far into that. I'll let Professor Fink cover that in great detail next semester with weld metallurgy. But I do want to talk about all of the various phase transformations coming from austenite, the austenite phase field, right? So if the max solubility is at the eutectoid point of 0.76%. And if we are below that, our equilibrium microstructure is going to be ferrite and perlite, right? If we're above that and we're in a hypereutectoid composition, we're going to have our final microstructure is going to be a mix of cementite and perlite. All right. We talked a little bit about orientation relationships, how the most important one in steel is the close packed directions in the FCC and BCC, or the 110 type directions in FCC aligned with the 111 type directions in BCC, and the 111 plane aligned with the 110 plane, right? And this is known as the Kurgyamov-Sachs orientation relationship, and is probably the most well-known, most important orientation relationship in material science. And because this has the lowest energy, it's going to appear all the time, right? And we said, I further went on to talk a little bit about aletriomorphic ferrite versus idiomorphic, right? And aletriomorphic, or grain boundary allotromorphs, nucleate heterogeneously on the austenite grain boundaries, where idiomorphic ferrite nucleates heterogeneously within the austenite grain at other inclusions, right? So the cleaner the steel, the less idiomorphic ferrite you're going to form. And the allotromorphic ferrite follows the grain boundary and it doesn't have any well-defined shape or structure or facets, whereas idiomorphic, because it's growing into the crystal, will have a faceted structure that corresponds to the generally the Kurdyumov-Sachs orientation relationship, right? All right, this is, and I left off by just mentioning massive ferrite, right? That if we have very low carbon content, in this case, ultra low carbon, 0.004%, that we can transform directly from the austenite to the ferrite without a change in composition. So in this case, the prior austenite grain structure is preserved, and we just have a local phase change. This doesn't require any long-range diffusion, right? Okay, so there's another morphology that we see in ferrite, and this is Wittgenstein ferrite, or a Wittgenstein microstructure. You see this a lot in meteorites, iron nickel type alloys. You see this in carbon steel when it is when ferrite is allowed to form at a slightly lower temperature. And the ferrite grows in these long, thin plates that when you make a 2D section, it looks like this interwoven basket structure. And they all have about the same crystallographic orientation. So this is very close actually to a single crystal, even though it doesn't look like it. It's just fingers of ferrite that are growing from different directions that have similar orientations. In fact, I was a little, when I said single crystals, not quite correct. Really what we have is, if the green face here is the growth direction, we've got a bunch of plates and they're all rotated about this growth direction like this, right? But they all have a very similar orientation with respect to the sample or the growth direction, right? This is an EBSD color map that tells you what the crystal orientation is. And what this says is all of this green means that these plates, these Wittgenstein structures, are all growing along with the 110 crystallographic direction, right? But that's not super important for here. What is important is the morphologies here. There's two ways that these Wittgenstein structures can grow. One is directly from the prior austenite grain boundary, in which case it's a primary Wittgenstein ferrite, or we can have Aletriomorphic Ferrite and the Wittgenstein can grow from that, in which case we have secondary Wittgenstein structure. And the interesting thing is, because we're at slightly lower temperature, it's not a purely diffusional transformation. And the reason I wanted to talk about this was because these Wittgenstein structures and the bainite have this dual nature where they're diffusional and shear at the same time, right? So we'll talk about Martensitic transformations as displacive phase transformations coming up, but there's a whole range of phase transformations that are sort of in between, where they're diffusional. They still require the carbon to partition out in the same way, but the mechanism of how the transformation happens isn't purely diffusional. the atomic planes slide past each other, and you have a corresponding transformation shear. Right? So I don't want you guys to get lost into the details here, right? But just keep in mind that not everything is ideal, right? Martensite is a purely shear transformation. There's no diffusion associated with martensite. The growth of grain boundary and idiomorphic and massive ferrite are purely diffusional. There's no shear associated with those. There's just the volume strain, that volumetric change that you get from going from austenite to ferrite. But a lot of other structures, a lot of other phase transformations that we see in material have a little bit of both. It's primarily diffusional, but we do have a macroscopic sort of displacement. So what happens in that case is, in order to minimize the energy in the overall displacement, we get two variants, crystallographic variants of this Widmanstätten ferrite that form where their shears are in opposite directions, so they cancel each other out. They grow as like this wedge, this sandwich wedge structure, so that when you average the shears together over both of these plates, it works out to be zero, right? They grow in a manner that is mutually accommodating and can lower the overall, reduce the overall Gibbs free energy and the activation barrier when they form together rather than forming individually, right? We'll talk about growth is next. So I'm going to come back to this on Monday after we talk about growth of precipitates, right? But this is just sort of what I wanted to point out, right? So at higher temperatures, we get a purely diffusional growth. At lower temperatures, we get this mixed mode growth. And at very low temperatures, we don't have enough activation energy. We don't have enough thermal energy for any diffusion, really. And so we form a purely diffusional, purely diffusionless, purely displacive, shear-driven martensite transformation, right? Okay. So let's go back to the talking about diffusional transformations, and let's talk about this growth of the nucleation and growth of perlite, because this is really interesting, right? So remember that if we come down, we're going to form ferrite from the austenite phase field. We're going to form ferrite and essentially pure carbon, right? So thermodynamically, graphite is the stable phase, but cementite is a deeply metastable phase when held below the eutectoid, and it is a complex unit cell, which is essentially an intermetallic. It has the composition Fe3C, iron 3 carbide, right?
I got a question.
Sure.
You said intermetallic. I've heard that word a couple different times. Is there a good definition of that?
So yeah, so I'll give sort of a colloquial definition, I guess, right? This might not be the most formal, but I think it's really useful, right? So the intermetallic is when you have two phases, or a compound that forms of two elements that in other regions of the phase diagram would make a completely metallic bonded system, right? So in the austenite phase field here, the carbon is all interstitial, and the primary, all the primary bonding is metallic, right? When we come down, now we get a, in this case, a carbide, a ceramic structure, where either the bonding is not primarily metallic, but primarily ionic or covalent. And intermetallics typically form with a distinct stoichiometry, right? So they will, in this case, it's iron 3 carbon. So they appear as line compounds for the most part on the phase diagram, right? There isn't a stable cementite width, right? There isn't a cementite region where you have a large composition variance, right? And so that's what really defines an intermetallic, I think, right? Is the fact that the bonding is either covalent or ionic, and it appears in a distinct stoichiometry, right? They tend to be very brittle, right? But yeah, that's it. Does that clarify?
Thank you.
Yeah. Right. So this cementite, iron C3, there's a whole bunch of other carbides that can form, but we're not really going to be worried about them. The equilibrium graphite phase tends to form at higher carbon content, right? And in that case, we're in the realm of cast irons, right? We're outside of what we normally think of as steel. And there's not a lot of really good technological applications for cast irons. So we tend to not spend a lot of time on those, right? Okay, so the important thing here is perlite is a composite, right? It's layers of cementite and ferrite. It's not a single thermodynamic phase, right? And it grows, it nucleates and grows into these really complicated layer structures, right? And in fact, the structure of perlite in 3D is much like a cabbage. It's like these layers that are wrapped up around themselves, right? So how does this structure sort of form and organize is a really interesting question, right? So this is obviously a hypereutectoid steel. This is grain boundary cementite, right? So we know that the white regions in here are cementite, and these darker regions are ferrite, right? So this is a steel with a higher carbon content than the eutectoid. Very rarely do we use hypereutectoid steels for anything, but okay.
I have another question. Back one slide. Yeah. All right. So this is a connection from previous lectures in the formation of the alpha and the formation of the beta, and they're kind of growing together, and it's this the diffusion. Does that ring a bell?
Yeah. So we'll talk about that, right? That's actually the main point I really want to stress with ferrite. Is the diffusional part. I mean, the perlite is the diffusional precipitation or diffusional segregation, and how that ties into nucleation and growth, right? because I'll talk about it schematically here, and then on Monday we'll analyze it a little bit. Right? So hold tight, and if your specific question isn't answered, then I'll hit me up in a couple minutes. All right. Okay. So we really have, there's two primary methods for how ferrite can nucleate, right? We can either nucleate as directly on the austenite grain boundary. So here's austenite grain 1, austenite grain 2, right? And we nucleate some ferrite and some cementite, and they grow in this alternating structure that has a corresponding wavelength associated with it, right? I mean, there's kind of a, this is schematic, but it's not too different from what happens in reality. There's a sort of regular separation distance of these cementite lamella, right? The same thing happens if we're hypereutectoid and we have a grain boundary cementite layer. Now we get cementite structures that shoot off, and we nucleate alpha next to them. But again, we keep a sort of regular structure, right? And so how does this come about, right? Well, it turns out we'll skip this, but there's two different orientation relationships that can form in perlite, depending on whether or not we're in a hypereutectic or hypoeutectic, and what nucleates first. Right? But this nucleation of the perlite colony, occurs by what's called sympathetic sideways nucleation of the ferrite and the cementite lamella. Right? So if we nucleate ferrite first, right, that ferrite has a very low carbon concentration relative to the austenite. So we need to partition a large amount of carbon out, right? So I've got a little nucleus here of austenite all around. I now have an elevated amount of carbon, right? Similarly, if I nucleate cementite, it's going to suck the carbon in. So around my cementite layer, I'm now going to have a region that is depleted of carbon. Okay? And remember, we're in a region where diffusion is pretty fast, right? We're just below the eutectoid kind of temperature, right? So the carbon can rearrange fairly quickly, but it's not instantaneous, right? The carbon is interstitial in the austenite, right? And we know that, so that means we're not dependent on vacancy diffusion. Interstitial diffusion is relatively fast compared to vacancy diffusion, right? But it still takes a finite amount of time, right? So we can probably speculate that the growth rates of these phases are going to be dependent on how fast we can diffuse carbon either away, right? If we were just growing the austenite, right, the growth would be slow, right? Because we'd have to move all this carbon far away. If we were just growing cementite, growth would be slow because I need to get carbon from far away here. But if I have them right next to each other, now I only need to get carbon from one to the other. Right? And that should sort of form the form the picture here, right? So essentially, as we're growing cementite, our carbon is depleted from our austenite, and it goes down. And eventually we get to a carbon concentration that's low enough that I nucleate a ferrite right next to it, right? I don't have to partition nearly as much. My activation energy to nucleate ferrite is decreased because my carbon concentration locally is much lower. The same thing if I'm growing, so now I nucleate ferrite on either side of my cementite. As my ferrite grows, I partition carbon out, and eventually my carbon concentration locally gets high enough that I nucleate new layers of cementite, right? And the amount, how fast it takes for this carbon to diffuse is going to be dependent on the temperature and the alloy composition, right? And that's what's going to set up my spacing. Right? So the spacing, the actual volume fraction of cementite and ferrite is given by the overall volume fraction, right? And the width of these ducts is dependent on how fast it can diffuse. So the perlite microstructure is going to be highly dependent on the composition. Right? I mean, yes, on the composition, obviously. What I meant to say is on the temperature. The temperature that this is growing at is going to determine the spacing, right? So if I'm at a high temperature and diffusion is easy, am I going to have wider or thinner cementite and ferrite structure, right? Am I going to have coarse perlite or fine perlite at higher temperatures?
At higher temperatures, I believe it's fine perlite, but I might be wrong.
All right. Okay, so for all of you saying fine, make an argument.
My argument is this. At higher temperatures, diffusion is easier to flow because that's the thermal gradient property of diffusion. So if it flows easier, it will make the... I don't know how to finish the argument, but you get the point.
Right.
Am I clear?
Right. So you can make an argument both ways, right? So if we just think about it for a second. So how can you make an argument that it would be coarser at high temperatures? Right? Right. So let's just think about this for a second and look at this picture, right? The width that this cementite is going to grow to before austenite nucleates is going to be dependent on how fast I can diffuse carbon from the austenite into the cementite, right? So the faster carbon is moving this way down this concentration gradient or chemical potential gradient, the longer I'm going to stay above this critical value and the wider my cementite's going to be. Right? And the same thing with the ferrite, right? The faster I can diffuse this in, the better, right? The wider my ferrite layers are going to be. On the other hand, I have to consider the effect of this moving interface, right? I have to consider my growth velocity, because not only am I diffusing in, but this velocity is moving out. This is moving out this way, right? Plus I'm growing this way as well, right? So it gets complicated, right? So I'm going to put this, I want just to throw out the sort of maybe the complexity of the system. And when we talk about growth on Monday, I'm going to come back to this, right? And we'll say what the answer actually is and why, right? But I want you to guys to think about it in your head until then, right? So perlite is spherical, right? We grow by adding lamellae or by branching, and by growth along the outward ends of the lamellae, right? And they're going to grow unimpeded until they impinge on adjacent colonies, right? Right. So what this tells you is that this perlite structure is not going to really have any relationship to the prior austenite grain size, right? It's going to completely erase the austenite microstructure, right? So if we're in a range where nucleation is difficult, right? We're not nucleating a lot of perlite. The ones that we do nucleate are going to grow large. And a perlite colony then can overtake the size of several austenite grains, right? Where's that going to happen? Where's our nucleation rate low? Right? At higher temperatures, right? At smaller undercoolings, we don't have a huge amount of driving force for nucleation, but growth is easy because we have a high temperature for diffusion. So that means we're going to nucleate very few perlite colonies, and the ones that we do nucleate are going to grow very large. Right? At lower temperatures, slightly larger undercoolings, we are going to have greater degree of nucleation, right? But we're not going to be able to they're not going to, I got to be careful how I say this, right? I don't want to speak too quickly and say something confusing, right? So if nucleation is easier, right, and we nucleate a whole bunch of perlite colonies heterogeneously on the grain boundary at roughly the same time, they're all going to grow until they impinge each other, and they're going to have a size that's smaller than the prior austenite grains. Okay? The growth rate also is going to increase with the driving force for transformation, the Gibbs free energy, the bulk Gibbs free energy, right? So we end up with a curve that looks something like this, right? With a maximal amount of growth, right? So our growth here looks very similar to our nucleation sort of rate curves, right? And we'll talk about this a bit more on Monday, right? So the size of the structure is going to be determined by this balance between nucleation rate and growth rate. Okay. Right. The nucleation rate depends, oddly enough, on the amount of time we hold at temperature. Right. And this is due to the fact we're nucleating heterogeneously. Right. Essentially, it takes a little bit of time for things to rearrange and to get our the microstructure to sort of get its ducks in a row for things to be able to nucleate, because we have to partition the first nuclei that form of either ferrite or cementite. Most of the time we're going to be talking about the first nuclei that form are ferrite. We need to move a very large amount of carbon out, right? So there's this dwell effect that we see in order for that to happen, right? And notice that dwell effect is not in the idealized nucleation theory that we talked about for heterogeneous nucleation, right? There was no time dependence in the equation for the rate of nucleation, right? But those are highly idealized, right? They make a good physical picture, but when you get down into the details of real materials, you see immediately lots of places where the ideal theory deviates from reality, right? And the fact that you have a little bit of a hold before and an gradual uptick in the in the nucleation rate over about 10 seconds or so here points just a little bit that the physical picture is more complicated than what we see, right? And so we have a scenario where the growth rate and the nucleation rate are both increasing with undercooling up to a point, right? So we have a point that's going to be about here where our growth rate is going to saturate with undercooling. Our nucleation rate keeps increasing with undercooling. Eventually, these will have to swing back, right? As we get to larger and larger undercoolings, they're going to swing back. But in practice, that doesn't happen in steels, because if we get to lower and stronger undercooling, we move away from the formation of perlite, and we will instead form either Widmanstätten or bainite structures. So again, that's another complication that the simple theory leaves out, right? We have to think about what happens with other transformations. But anyway, we can see here the growth rate is going to reach sort of a maximum with undercooling. The nucleation rate increases, right? So when growth is faster than nucleation, we're going to get very large perlite colonies. When nucleation is faster than growth, we're going to get lots of very small ones. Okay. Right. And so that's what I wanted to talk about with perlite. And the last couple seconds, I just want to introduce, I'm not going to talk about it in any detail. I want to talk about another intermediate between pure diffusion and pure shear, bainite, right? Bainite is a shear transformation, but we also have carbides that form in between, right? So we end up with these layers of ferrite with carbides, cementite, and other types of carbides in between, right? And this is a two-step process. We have a little bit of diffusion followed, well, whether or not we have initial diffusion is still sort of a debated topic, but then we have, so then we have a shear transformation and then diffusion to form the carbides in between, right? We're going to come back to this after we talk about martensite, but bainite, you see, this is a atomic force microscopy that gives us very good surface profiles, right? And you can see we get steps at the interface when bainite forms, right? So that means that there's a very large shear associated with it, right? And as it shears, we also have martensite. I mean, not martensite. We also have plastic deformation that occurs, right? So these real phase transformations get really, really complicated, right? And it's very difficult to tell whether or not you're looking at a microstructure, whether something's bainite or martensite. Sometimes it looks like Widmanstätten and it's actually bainite. Sometimes it looks like martensite, but it's actually bainite. And there's still sort of a debate as to whether or not bainite is diffusionless or diffusional, right? We'll get into that debate when we talk about martensite, right? But I just wanted to throw it out. A lot of you guys have probably not talked about bainite much, or Widmanstätten ferrite for that matter. But the main thing really is that nothing is ideal, right? We talk about this beautiful theory in the book, but in reality, everything's muddy and confused. And nothing actually follows the theory to perfection, right? So the takeaways from today's lecture are the sympathetic sideways nucleation, right? The relationship between nucleation and growth, right? We have to talk about the growth on Monday, but things are sort of intertwined, and that in real materials, things are very rarely purely diffusional or purely shear. And the idealized equations that we talk about are just idealized equations. They give us the right physical picture, but often they're not true quantitative reality. Okay. So have a good weekend. Stay safe. Stay, things are getting bad out there. So, do your part to stay healthy. Okay. You don't want to be bringing COVID back home with you when you go for Thanksgiving. So stay safe, stay healthy, and we'll see you guys on Monday.